Hey there and welcome. We're about to dive into something you feel every single day, from the warmth of a coffee cup to the chill of a winter breeze. I'm talking about heat. But have you ever stopped to wonder how it actually gets from one place to another? Well, in this explainer, we're going to follow its invisible journey.
Let's start with a classic kitchen puzzle, a pot of water on a stove. The flame's way down at the bottom, but somehow the water at the very top gets boiling hot. Seems simple enough, but what's really going on? How does that heat energy travel all the way from the flame, through the solid metal of the pot, and then up to the very top of the water? Let's figure it out.
Okay, to answer that question, we first need to wrap our heads around one single fundamental rule that controls everything about heat. Seriously, this one principle unlocks everything else we're about to talk about.
At its core, heat is all about finding balance. You can think of it like a one-way street. Energy always flows from a hotter object to a colder one. Always. It never, ever goes the other way around. And this flow keeps going until both objects reach the exact same temperature. That balanced state, we call it thermal equilibrium. This simple experiment shows that rule in action perfectly. The second that hot metal block hits the cold water, you can almost picture the energy just pouring out of the block and into the water. The block starts to cool down, the water starts to warm up, until, bam, they meet right in the middle, perfectly balanced.
All right, so now that we've got that fundamental rule down, let's look at the first way heat gets around. This is what happens when things are in direct contact, a process that scientists call conduction.
So, what's happening on a microscopic level? Well, it's pretty cool. The tiny particles in the hot part of an object are just vibrating like crazy. They start bumping into their neighbors, and those neighbors start vibrating and bump into their neighbors. It's like a tiny domino effect that passes energy down the line, which we feel as heat.
Of course, not all materials are equally good at this game of dominoes. Metals, for example, are fantastic conductors. Their particles pass that energy along really efficiently. That's why your frying pan is made of metal. But then you have materials like wood and plastic. They're insulators, which means they slow that transfer way down. And that's exactly why the pan's handle is made of plastic, to protect your hand from all that heat being conducted by the metal.
So, conduction works great for solids where particles are packed tightly together. But what about things that flow, like liquids and gases? How does heat travel through them? Well, that requires a completely different and way more dynamic method. In fluids, and that's just the sciencey term for both liquids and gases, it's not about particles just bumping into each other anymore. In this case, the heated particles themselves actually start to move, carrying the heat with them from one place to another. This movement creates these amazing patterns called convection currents.
And we see this everywhere. Think about a heater in a room. It warms up the air right next to it. That hot air becomes less dense, so it rises. As it rises, the cooler, denser air from above sinks down to take its place, gets heated up, and then it rises too. This constant circular flow is a convection current, and it's what eventually warms up the whole room. The exact same thing happens in nature, creating things like land and sea breezes.
Okay, on to our third and final method. And honestly, this one is kind of mind-blowing because it explains how we can feel the warmth of the sun even though it's 150 million kilometers away across the cold, empty vacuum of space.
This is radiation. And unlike conduction or convection, which need particles to pass the heat along, radiation doesn't need any matter at all. It actually travels through the universe as invisible electromagnetic waves, kind of like how light travels. It's pure energy on the move.
And these heat waves are fast. I mean, unbelievably fast. They travel at the speed of light, a staggering 300,000 kilometers per second. It's because of this incredible speed that the sun's energy can zip across the solar system and warm our entire planet in just about 8 minutes.
So, there we have it. Our three methods: conduction by touch, convection by flow, and radiation by waves. But here's the most important part. In the real world, these three almost never happen by themselves. They're almost always working together as a team. To see how it all fits together, let's go all the way back to the beginning, back to our pot of water on the fire. We asked how the heat gets from the flame to the water at the top. Well, now we have all the pieces to solve that puzzle.
First, the fire radiates heat waves through the air, warming up the outside of the pot without even touching it. Then, conduction takes over, as that heat travels through the solid metal of the pot's base and up its sides. And finally, inside, the water at the bottom gets hot, becomes less dense, and rises, kicking off a convection current that swirls around and distributes the heat through all of the water. It's a perfect three-part system.
So, the journey of heat isn't just one simple story. It's three amazing stories happening all at once, all around us, from a spoon in your mug to the winds that circle the globe. So the next time you're in the kitchen making a cup of tea, take a closer look. Can you spot that invisible dance of radiation, conduction, and convection happening right there in front of you?